Okay, time to get started. So here's here's what we were talking about last time. It's not true. Here's something that I've skipped over last time. Well, here's a reminder of something that we did talk about recently that's going to segue into something that I skipped over last time. So that's the right introduction. So reminder, what we talked about a long time ago, fundamental theorem of calculus, right? And if you choose to view this as an accumulation of a thing, a stuff, a quantity that I like to call change, right? Then along those lines, making the analogy to how this integral looks a lot like this integral, then by the analogy, derivative can be thought of as a kind of a density. And in the same way that, this lowercase delta here represents what we commonly call mass density, likewise, it makes sense to call the derivative change density. And that makes a lot of sense in, if you come back to this picture, this picture here, looking at how accumulation of change happens. And so specifically, while you measure change on the boundary, and that's where you measure it, right, and you detect this difference by looking at the values on the boundary, well, it's perfectly obvious that that's not where the change actually happens. The change actually happens in the interior. Right? Couldn't be more clear. Look at the picture. Right? Here's where the change is actually happening. It's happening on this range of values of x because, bam, look at that. That's where the change happened. Right? So the derivative is a way of measuring where is that change happening. The accumulating quantity that we measure on the boundary, where and to what extent in the interior is it really happening, measured by this derivative, the change density. Okay, so I want to point out, was what I skipped over last time, was that you can make an analogous argument. We already talked about it in the context of the divergence theorem. Again, divergence, along those same lines, interpreted as flux density. Well, let's make this same argument in the context of Green's theorem. And we kind of skipped over this. And it turns out it makes for a nice segue into what we're going to talk about next today when we get to Stokes' curl theorem. So anyway, for the moment, let's talk about Green's theorem. Here it is. And let's take the same sort of point of view. Here's what we're kind of computing. We're computing a line integral around the boundary. That's the object that we're measuring. We argued when we wrote down Green's theorem in the first place that this boundary line integral thing accumulates, right? This is an accumulating quantity. I mean, you measure it around the boundary, but you can view it as the sum of similar expressions over the interior. So now, before I go on and finish this argument, let's give a name to this. What should we call this? Boundary line integral. And the proposal that I'm going to make here requires a little bit of a justification. Here's that looks too much like a circle. It doesn't need to be a circle. Here's a boundary. And here is an orientation on that boundary. This is the positive orientation on that boundary, counterclockwise. And what does a line integral represent? Well, we talked about how line integrals represent the extent to which the field is kind of pointing along the curve. And that's the sort of the fluid's point of view on what line integral measures. To what extent does the fluid flow along the curve? And my modest proposal here is that, well, look, if we're measuring how much the fluid is flowing along the curve, and if the curve is in the process of making a loop, that means the curve is in the process of going all the way around, making a sort of a full turn. The extent to which the fluid does that same thing means we're kind of measuring the extent to which the fluid is making its own kind of loop. It's like we're measuring to what extent is the fluid sort of flowing around, right? If the fluid's following the curve, and if the curve's making a complete loop, it's like we're measuring how much the fluid's doing the same thing. So anyway, so the term that we use along these lines is circulation. And so this quantity that we measure, this accumulating quantity that we're talking about in Green's theorem, very commonly referred to as circulation. I think it's a lovely name. It's just borderline perfect. kind of describing what it is that, this boundary line integral is measuring is, again, the extent to which the fluid is kind of doing something like that. Okay. I hope that's plausible. Circulation accumulates. That's a rephrase of something we talked about when we were justifying Green's theorem. Circulation accumulates. Circulation accumulates over the interior, like so, kind of in the same way that mass accumulates over the interior, like so. And along those lines, you can think of Green's operator as being a kind of a density. So this is totally analogous to what we argued on the previous page, totally analogous to this, in the same way that you can think of the derivative as being, in the context of the accumulation of change, you can view the derivative as being change density. Likewise, you can think of Green's operator in the context of thinking of circulation as an accumulating quantity. You can think of Green's operator as being circulation density. So anyway, I think it's a nice point of view, nice sort of physical, geometric anyway, but I think, again, mostly physical way of thinking about what Green's theorem is actually talking about. And before today, we didn't really have a sort of a physical or geometric metaphor for Green's theorem. So here it is. Now, by the way, there's another word that gets used to describe, what it is that Green's operator is measuring. That word is vorticity, based on the word vortex. Vortex being a little tornado where air is spinning around. I mean, it's a pretty plausible choice of words, right? We're kind of measuring to what extent the fluid is behaving like a little tornado. So anyway, you'll hear that term as well, and I think it makes a lot of sense too. Okay, I think I'm probably going to use circulation density more in this class because I'm all about the metaphors and the analogies and seeing connections between things. And circulation density is easier to relate to terms like flux density and change density, right? And so just the construction, the grammatical construction is more consistent with what I'd like to do. But anyway, out in public, you'll hear both, but out in public you might hear that one. All right. So this turns out to be a pretty good segue into what we're going to talk about next. We're going to talk about Stokes' theorem, Stokes' curl theorem. And I'm going to vaguely say something to do with what we're talking about here. Right? So now let me just sort of plant that thought, and we'll come back to it in a few minutes. And now I'm going to move on past all this Gauss stuff that we did last time, and here we are, attempting to talk about Stokes' curl theorem. And let me remind you of our context. We're in R3. Of course, Green's theorem's in R2. Now here we are back in R3. Let me remind you that when we were talking about the fundamental theorem of line integrals, we took a curve and looked at the boundary points and plugged in and then asked, can I view that as a line integral? Can I view that as a line integral by applying some operator to the function to get a vector field, over which a line integral gives me the same result? And then, in R3, we looked at the regions and their boundary surfaces and computed a flux, just following the pattern on the diagram, and then asked, can I view that as a triple integral? Is there some function that I can in some way derive from the vector field whose flux I just computed? Is there some operator I can apply to that field to get a function whose triple integral gives me the same value? So you'll notice that we kind of skipped over, we applied the idea here, we applied the idea here, we kind of skipped over this middle spot. And here we are. We're going to fill in that middle spot. And so let me just write it out again. We're going to look at a surface and its boundary curve. On that boundary curve, we're going to compute a line integral, because the diagram tells me to, right? We're going to compute that. We're going to write down that line integral, and we're going to ask, can I compute that line integral as a flux? Specifically, is there something that I can do to that vector field whose circulation I just computed? Is there something I can do to that vector field such that the resulting flux is the same as that circulation? So that's going to be our goal. We're going to look at a line integral around a boundary. So by the way, let me go ahead and invoke our new term, circulation, right? We're going to look at a circulation around a boundary. It's kind of implied with the term circulation, but anyway. We're going to look at a circulation and ask, can I view that circulation as accumulating, and can I further view that accumulation as a flux? Okay, so let's just start playing the game. Here's the original surface. Here's the boundary. The boundary of that surface. Now notice my surface is oriented. Right? Got a normal vector there. Recall that when you say boundary of an oriented surface, that gives you an orientation on that boundary curve. So I've indicated the orientation here, and it's remember the right hand rule. So you thumb in the direction of the normal vector and look at the way your fingers kind of swirl around, etc. Okay, so we're going to look at this circulation, and I would like to ask, is that circulation the sum of a circulation around that little piece plus a circulation around that little piece? And these pictures get a little tedious, right? So is it a sum of that circulation plus, adding up all of these circulations? So do circulations, on surfaces in 3 space, do circulations accumulate is our first question. And hopefully no surprise, right? But here's the picture. Again, just, sort of for motivational purposes, I'm going to start with an easy case of a surface that I'm cutting just into 2 pieces. Here's a rectangular, bent. This is a surface, right? So it's allowed to be bent. So here's a bent, kind of rectangular-ish surface, oriented up. So I've got drawn here. And I'm going to chop it into 2 pieces and ask, is the boundary that I just wrote, is that equal to this boundary of S1 plus this boundary of S2? That's what it would mean for circulations to accumulate. Again, you can see it mostly checks out. All of these pieces here are going the correct direction. The worry is, when I sliced, I created kind of what you might call 2 new edges. What happens to those 2 edges? The line integral on those 2 edges, that might make, the sum, the yellow circulation plus the green circulation not add up as it's supposed to. So the question is, on that boundary, what's going on? And of course, you can see this coming, but as part of the boundary of S1, that edge is oriented that way, and as part of the boundary of S2, that edge is oriented that way. And so in the summation, this curve appears twice, but it appears twice with opposite orientations, and therefore those 2 terms cancel in the summation. So I hope this looks familiar. Right? I could literally view this diagram as having come from taking the page in the book on Green's theorem and just kind of bending the page a little bit. Right? It's morally equivalent to the argument in Green's theorem, and it's structurally equivalent to the analogous argument we made in the context of Gauss's divergence theorem and of the fundamental theorem of line integrals. Right? So new terms, opposite orientations cancel. Yeah. So is everybody happy with this? All right. Again, a nod of appreciation to these arbitrary conventions that we made about what directions boundaries are oriented. Right? Arbitrary rules that we made about whenever you say boundary, always orient a certain way. Always counterclockwise, or always plus at the end, minus at the beginning. These arbitrary rules that we made up are what make these cancellations happen. So now you can see why those arbitrary rules were important. Okay, so let me just go ahead and recognize this. This page of the book looks really scary when you first look at it. All right, look at all those scary-looking symbols. Okay. But it's the same argument that we've made on many occasions. So let's just walk through this and see how this really all goes directly through. So we just got through observing that circulation accumulates. That's all this says. Circulation around the boundary of the whole thing is a sum of the circulations around the boundaries of the pieces that you slice it up into. Right? So that's just a rewrite of what we argued on the previous page. The limit is for free because this is independent of I. Independent of n. It doesn't matter how many pieces you slice this up into. It's always equal to the same value. Therefore, what we're talking about here is a limit of a constant, and a limit of a constant is that constant, so that we can put the limit in for free. Does this look like a surface integral? Well, not really. We want it to look like a surface integral, so we multiply and divide by delta S. Now this is looking a lot like a surface integral. Bad news, we don't happen to recognize this expression. Right? Circulation per unit area is not something we've already seen before. So what? It doesn't matter that we don't happen to recognize it. A peculiar and not really that important bit of good fortune from when we were doing the fundamental theorem of calculus is that we happen to get lucky and recognize the analogous quantity at this stage. But it doesn't make any difference. The point is this is still something that I can compute. This integrand here, and again, there's details, and I don't want to go into the weeds on exactly how this works, but this integrand can be computed, and here's a formula for it. And exactly where the formula comes from is not as important as the fact of where it comes from. It comes from this idea that we're looking at circulation per unit area. We're accumulating circulations over a surface, and on each little bit of area, we want to know how much circulation is happening per unit area at that location. Okay, so that's the most important thing, and exactly how you get there, not so much. Okay, so knowing this formula, let's plug this into there, and that makes our integral become this. We have that formula. Let's just plug it in. And then a quick last step, let's not forget that in ds is our ds vector. And so lo and behold, as we were sort of hoping, we have found that yes, circulation, not only does circulation accumulate over the surface around which you're moving, but circulation accumulates as a flux. It's a flux of this wacky vector field here that we'll talk about momentarily. Yep.
So what's like a physical?
Yeah, we'll get to that. Yeah. But, the closest thing that I can give you, right now, and really this is what I'm going to give you later as well, is that this thing is a way of measuring that. It's a way of measuring circulation per unit area. Roughly speaking, there's some details I have to worry about concerning the little normal vector there. But circulation per unit area, circulation density. Right? In other words, as these little pieces of area get smaller and smaller, well, of course, the circulations are going to get smaller and smaller because they're really short curves. The vector field is increasingly constant, and there's just not that much room for it to twist inside of there. And the curves are getting shorter and shorter. You sort of doubly expect circulations to get smaller as the pieces get smaller. But the area is getting smaller too, and so if you say, well, how much of this shrinking circulation is there divided by the shrinking areas? So circulation per unit area, right? So in the same sense, I know I spend a lot of time on the analogies, but I think they're so valuable. When you talk about change density, sure, as your domain gets smaller, the change gets smaller, right? The rise gets smaller when the run gets smaller. So as these things shrink, sure, the change approaches 0, but so does delta x, and the proportion, though, that I like to call change density, and most people like to call slope. Right? You expect to, it's possible that could converge on some reasonable limit. All right, great question. So there's a fuller discussion about that I want to delay until after we've kind of gotten the theorem written down. I want to get a couple of examples under our belt, and then we'll start exploring the pictures. Okay, so this object here we call curl. It's just a name, kind of like divergence is just a name to describe the integrand that we ended up with in Gauss's theorem. So this is called curl. Again, it's kind of vaguely reasonable as a terminology. I mean, curl suggests how much is the. I mean, come on, this is the. How much is the fluid kind of? I'm doing the hand gestures deliberately, right? So we're trying to get our handle on this idea of the fluid kind of spinning around, right? Conceivably, they could have, way back when, referred to this as spin of F. That would have been a reasonable choice as well, but they didn't. They called it curl. So there we are. Okay. Curl. And again, there's a notation for this that's very convenient that a lot of people use, mostly physicists and engineers, and that is to observe a relationship to the del operator. Don't forget the del operator. We talked about the del operator with divergence. You could view the divergence as del dot F, as it turned out. Well, check this out. If you were to take the del operator and your vector field, and if you were to take the cross product. Remember, cross products proceed by way of taking a symbolic determinant. So this is a really symbolic determinant, right? Because not only is the first row made up of not real numbers, right? The first row is made up of vectors. That's weird. Not really supposed to do that. Not really supposed to. That's not what a matrix is that we've previously conceived. Not only is the first row kind of messed up, that second row is kind of messed up too. Those aren't real numbers either. And those are operators. But if you just go ahead and just let it slide, this is just notation. If go ahead and be flexible about it. If you were to take the cross product of the del operator and the F field, look at what you get. You get exactly what on the previous page we've already designated as curl. That's just lovely. This works out. So this is a very common alternative choice of notation to write del cross. You'll see this all the time in physics class. Well, correction, I saw it all the time in physics classes. I assume they haven't changed their norms and hadn't been that long. And I assume engineering would be similar. So anyway, heads up. So anyway, that's how I'm going to write the result here. So, again, we started off with we're going to take the boundary of a surface. We're going to look at the resulting line integral, and we would like to ask, can I view this as a flux? Is there something I can do to my original vector field F to give me a flux that will compute that circulation? And, it's called the curl operator. There it is. We'll append our diagram. We now have a new entry in our diagram, right? This curl operator is sort of, if you will, complementary to the boundary operator in this usual sense. Yep.
So, obviously, there's this really big similarity between Gauss's divergence, where we looked at the del dotted to the vector field, and now we're looking at curl, which is del cross into the vector
Which just happens to be, that's right.
And is that coincidental? Was there geometric
I'll bet you there's nothing in math that's truly a coincidence. But as far as we're concerned for Math 212, let's just call it one. It's not something I'm going to be able to make any sense out of in this context.
It's not something where we can say that there's something going parallel for one and going for...
No, nothing like that. Nothing like that. Yeah. I mean, I see where you're coming from, and yeah, it's not like that. Yeah, right. But it's a reasonable speculation. Yep. So for the purposes of this course, let's call it a coincidence. Yeah. Okay. Here's Stokes' curl theorem. Again, as you all know, I like to write the theorems separately so that we can have a complete diagram, up here. And so we now have our brand new operator in that position. Don't forget, we already put divergence there. We already put the gradient operator there. And so, by the way, we've kind of completed our R3 diagram. So I'm going to switch over to page 449. Which we'll get to, I guess, tomorrow, right? And here's our R3 diagram, and it's pretty much all put together. I am going to add some more stuff to it that I haven't really talked about yet. But in terms of our original plan of, can we take this that we wrote down in section 6.1? Well, minus. We wrote down everything except for those in section 6.1, and we asked, are there are there versions of the fundamental theorem of calculus that sort of attach to this diagram in the same way that the fundamental theorem of calculus is attached to the R1 diagram? And we're done doing so. And yes is the answer. There is a fundamental theorem of line integrals that comes from the gradient operator. There is a theorem here. Stokes' curl theorem comes from the curl operator, and there is a Gauss's divergence theorem, we call it, that comes from the divergence operator. So, done. Some feeling of satisfaction and completeness that comes from getting to this point. Okay. All right. So let's do some examples. Now, there's a bunch I have to say yet about what curl looks like. We will come back to that momentarily, but I do want to get some examples under our belt. Suppose we want to compute this line integral. Here's a vector field. There's a curve. The curve is, in fact, already parametrized. Let me remind you that when you are called upon to compute a line integral, the question will probably not say, and I want you to do it by the following method. Right? Certainly in real life, it doesn't come up that way. Line integrals just show up. Hey, we need to compute this line integral. No hint as to how. Right? So when you compute a line integral, you have to decide now, do I want to chapter 5, parameterize and plug and chug? It's an option. Do I want to try to use the fundamental theorem of line integrals? Maybe. Here we're going to entertain the third possibility, which is, hey, maybe we'll be able to compute this with Stokes' curl theorem. By the way, just for your curiosity, if you did try to do this integral with the fundamental theorem of line integrals, it would fail. And you're welcome to explore that possibility. But if you try to find an anti-gradient, losing. There is no anti-gradient. So fundamental theorem of line integrals crashes and burns. You could parameterize. In fact, it's already parameterized, right? So you could use the parameterization, plug in, pull back per chapter 5. That will work, but it's not exactly the easiest integral in the world. It will go, but it's not anywhere near as easy as what I'm about to show you. Yeah.
Are you gonna tell us that little trick about?
Yep. Oh yeah. So I am currently concealing a trick for how to decide without playing the game and losing when it is that a vector field does or does not have an anti-gradient. It's a very cool trick, and we're going to get to it in pretty soon. Possibly today. I can't remember what I decided. But anyway, very soon. Yeah. Okay. All right. Now, I want to point out that Stokes' curl theorem comes with an asterisk, as all of our previous theorems do. Like the fundamental theorem of line integrals, the asterisk is the vector field has to have an anti-gradient, and not every vector field does. Right? Gauss's divergence theorem, if you're going to compute a flux, asterisk, the surface has to be a boundary. It has to be a closed surface, therefore the boundary of some solid, because you need that solid to do the resulting triple integral. So, and this is a very significant, often deal-breaking condition on being able to use that theorem. So likewise here, there's a big condition. We want to compute a line integral. If I'm going to be able to apply Stokes' curl theorem, and you can see it right here, that curve has got to be the boundary of some surface. I mean, whatever my vector field is, I can compute the curl, fine. That's just some derivative. We know we can compute derivatives. I mean, assuming the vector field's nice. But not all curves are boundaries. And by quite a bit. There's plenty of curves that aren't boundaries. Here's one. There's a curve, not a boundary. Right? We need our curve to start and go along and then end at the same point so that it is a boundary of a surface on the inside. Okay, so if we're going to just say Stokes' curl theorem, I mean, it would be totally irresponsible to just assert, I feel like using Stokes' curl theorem, right? We've got to confirm that this curve actually is a boundary of something. So, well, let's draw that curve. The curve is given as a parameterization, and let's see here. It's it's cosine and sine in the xy plane. Z is 0. This is in R3, isn't it? So cosine and sine. T goes from 0 to 2 pi. It's pretty easy to persuade yourself that our curve looks like that, and it does indeed start and end at the same point. Yeah.
Going back to like the requirements for this to work. Isn't it the same thing for Green's theorem?
Yep.
Okay.
Absolutely.
So
Absolutely.
Are Stokes' curl theorem and then Green's theorem?
They have a lot in common. Yeah, a lot of people like to talk about Green's theorem as being kind of Stokes' theorem in 2 dimensions, and there's a point of view there. Yeah, I like to think of them as different theorems. They were certainly derived. They historically they came up independently, and there are important. I mean, Green's operator gives you a scalar. Curl gives you a vector. Right, so I mean they're pretty different in a lot of ways, but yeah, they have a lot in common, absolutely. And you can think that there was a lot of strong analogies there, totally. Okay, so this curve is a closed curve. Now, by the way, let's suppose you couldn't just draw your curve as easily as we could here. How could I tell if this is a closed curve? Well, you can kind of directly compute. You can take t equals 0, plug it in. You can take t equals 2 pi and plug that in, and notice that you get the same point. Right? You don't have to draw anything to see that this parametric curve starts and ends at the same point. And then you think to yourself, I mean, if it starts somewhere and goes off and comes back, it starts and ends at the same point, closed curve, surface. I'm going to put an asterisk on that statement as well. There is a little issue that I've got to address that I'll get to later. But anyway, that's a sort of an algebraic workaround. Okay. All right, so closed curve. And that means that this is the boundary of a surface. For example, that surface. Now let's worry about the orientations. My curve comes with an orientation. My curve goes that way because that's, as you increase time, that's the way that this is tracing this curve in space. So I need to put an orientation on my surface in such a way that's consistent with this. And if I make the mistake of orienting down, thumb, fingers, swirl, this doesn't work, right? So you cannot just orient this surface however you feel like. You've got to pick correctly. What is the correct orientation? And it depends on what's the orientation of your curve. You can't just say, oh, well, everything's supposed to be up. It's not. Right? So in this case, it happens to be up because that's the choice of orientation on this surface that has your fingers going the correct direction and thus giving you the correct orientation on the boundaries. Everybody see how that's important, right? If this curve had been going the other direction, then it would have to be down. Okay. Right. Okay, so there's that's what I'm going to call our surface. Now, I do want to point out that this is not the only surface. You could pick a bent surface like this, kind of a, if you will, a hemisphere. If you think about it, the boundary of that hemisphere is that curve. Right? In fact, you don't even have to pick a particularly nice surface. I like to always talk about the glove. Right? Just imagine a glove. The hole that you put your hand through could be that curve. Right? So there's lots of different surfaces that you can pick. So think with as much creative laziness as you can invoke, right? What would be, of all of these different possible surfaces, which one would be the easiest surface to deal with? And not always, but most of the time, the easiest surface is the obvious surface. In this case, this flat plane. And that's the one I'm going to use in this case. Everybody on board? All right. So, So, the curve is a boundary of a surface. Therefore, I can invoke Stokes' curl theorem. Now, how do you compute curl? Okay, well, that's just, you just got to write down, partial with respect to x, partial with respect to y, partial with respect to z, and then play the usual game with determinants. The first component is going to be the y partial of that minus the z partial of that, which is 0. Right? The second component is going to be the z partial of that minus the x partial of that, which is also 0. And then the third component is going to be the x partial of that. Oh, there's a 1. And then minus the y partial of that, I'm subtracting a negative 1, and that gives me 2. Everybody see what happened there? Just computing the curl. But remember, curl is this symbolic cross product, therefore a symbolic determinant, and therefore is computed by this little trick. I like this little trick because in my mind I've gotten to the point where I don't even have to write this down. I can just visualize those little partials being there, and I can think to myself, okay, all right, well, first component, y partial of that minus z partial of that, and boom, and then just keep right on going, right? So I find that convenient. Okay, anyway, we have taken our line integral, our ugly-looking line integral. We have invoked Stokes' curl theorem. We've rewritten it, therefore, as a flux. This is an easy flux because don't forget our normal vector is like that. It's pointing straight up because our surface is flat, therefore our normal vector is straight up, which is easy to write down. It's 0, 0, 1. Right, now we have a super easy integral. Integral of 2 over an area, barnyard variety, geometric figure. Answer is 2 pi. Everybody on board? All right, let's do a different one. Okay. So let's see here. Here we go. We're going to compute a line integral. Got a vector field given. The curve is the intersection of these two surfaces with a given orientation. Now, so we got to draw the picture here. We were not given a parameterization. It's not immediately obvious what this curve looks like. We need to draw the figures. And so that plane, that cylinder, something like this. Right? So we have a plane intersecting with a cylinder, and I appeal to your sense of, what happens when you take an angled cut on a tube, right? Buy a straw. Take straws you already have. You're supposed to cut those up anyway, I think. And you get this curve. So that's our curve. Now wait a second, we were told in orientation, oriented counterclockwise as seen from above. So, okay, as seen from up here, and just, imagine yourself looking down on it from that perspective of above, counterclockwise. And that means it's going that way on the near side. Here, let me do this with a better color. It's going that way on the near side, and that way on the far side. Yeah? Okay. All right, so there's a curve. Now, again, if you want to parameterize the curve, go ahead. It's not clear that would be a bad choice. Look at our vector field here. That's not a bad vector field. X and Y are easy to parameterize. Sines and cosines. It's easy to solve for Z. Z is just X. It'd be pretty easy to write down a parameterization and pretty easy to do a plug-in pullback to compute this line integral. Not a throwaway concept. Could very well work out that that's the best way to do it. Anyway, let's call that plan B for the moment, and let's consider the possibility of using Stokes' curl theorem. I need to first confirm, as previously discussed, that this curve, come on, I need to do better than that. This curve is a boundary of some surface. No problem. It's the boundary of that surface. Or that surface. I don't know why I'd want to make things more complicated, or, all sorts of surfaces we could pick. Again, channeling our creative laziness. That's about the easiest surface that I can think of. That's whose boundary is that curve. Everybody happy with that? Okay. Now, our picture then tells us some very useful information. The surface that we're interested in is on this plane, which has this equation that's given. And therefore, this is my normal vector, and there's a typo here. I need my vector to be a unit normal vector, so I have to say divide by square root of 2. Sorry about that. So there's our normal vector. Yeah. Everybody happy? Now I just swept a little subtlety under the rug. Anybody notice the little subtlety that I just glossed over? Got to worry about orientation. Oh yeah, go ahead.
Oh, yeah.
I gave it away. Yeah. Yeah, so you got to worry about the orientation. Yeah, exactly. So, why didn't I write down 1, 0, negative 1? Because you got to think about orientations, right? Remember, we agreed that this curve was given oriented that way, sort of counterclockwise as seen from above, and sure, it's at an angle, but that means that the normal vector has to be somewhat in the up, so what I like to call up-ish, right? The third coordinate of our normal vector needs to be positive, and so that's why I put a minus sign on, instead of writing down, as I naively would from this expression here, instead of writing down 1, 0, negative 1, that'd be downish. We can't have downish, it's got to be upish, and so, therefore, the minus sign. Okay, all right. So anyway, there we go. And we write down Stokes' curl theorem. The curl easily computed. That's algebra. I'll let you guys do that algebra for yourself. It's this, negative 1, negative 1, negative 1. Let's see here. Our normal vector, we just argued, is that divided by the square root of 2. And so by using Stokes' curl theorem to turn this line integral into a flux integral, what we find is that we're doing a flux of the 0 vector field, and that's a really easy flux to compute. Flux is 0, and we're done. So parameterizing and pulling back would have been not so bad, but in this case, Stokes' curl theorem is even better. Everybody happy? All right, so let's move on now and talk about how do we think of. Oh, by the way, there's an example here relating Stokes' theorem to Green's theorem. Somebody asked about that. I guess it was you. So there is a nice way to connect Stokes' curl theorem and Green's theorem. It's all right here in this example, and I encourage you to take a look at it. But that's something y'all can read on your own. So let's talk about how to think about curl. What does this look like geometrically? What is it a density? Can I just call curl circulation density and be done with it? And not quite. In fact, I'm going to start with a discussion about a related idea, which is I'm going to go back to the fundamental theorem of line integrals. I don't know if you noticed this, but when we were talking about the ideas of densities, we talked about the fundamental theorem of calculus. We talked about Green's theorem. We talked about Gauss's theorem. And I kind of didn't mention the fundamental theorem of line integrals. I just kind of didn't include that. And there is a reason that I didn't include it. It's because there's something qualitatively different about how that point of view comes off in thinking about the fundamental theorem of line integrals. So anyway, I wanted to have that be a separate discussion, and here we are. It turns out that this segues in a wonderful way to Stokes' theorem. So anyway, here's the idea. Let's look at, here is our fundamental theorem of line integrals, which, as you'll recall, I want to think of as change being computed with the line integral. I'm writing the line integral here as gradient.tds, alternative notation. So there it is. Now let's draw a picture. I'm going to imagine that this is all happening in 2 dimensions, just for sort of artistic convenience. I'm going to draw a bunch of level sets of my function, and let's say we're looking at this point here. So that's where we are. And let's suppose that we're moving along a certain curve. See, I'll use this to represent my curve. Now the curve that I'm moving along could be going in any direction. Right? The level sets of my function don't dictate to me what directions I'm going. Okay, so let's talk about now, can I view, as you might expect, can I view gradient as being change density? And I argue that, well, not quite. Not really. Right? What is it that relates change and size? Well, it's, change per unit size is not the gradient. Change per unit size is gradient dot t, not gradient by itself. Right? So, okay, well, what's going on there? Why is this different? Well, here's what the gradient vector looks like. Remember, gradient vectors are always perpendicular to the level sets. There's the gradient. And could we at all reasonably suggest that a vector is a density? That doesn't even make sense. Vectors have a direction, right? Densities are fundamentally scalar quantities. Densities are stuff quantity, right? Divided by size quantity. Right? So we think of densities as scalars. So the gradient vector is just not really set up to be thought of as a density. But gradient dot t, there's my unit tangent vector. That is, right, this dot product I can think of as a density, like so. So okay, fine. But I don't want to have to go around talking about gradient.t all the time. I would like to have some... gradient is the object I'm interested in. How can I think of gradient? How does gradient relate to density? It turns out there's a great answer to this question. Gradient actually tells you 2 things. Gradient tells you, for one thing, how fast is the function increasing in the maximal direction. So how steep is the mountain in the uphill direction? Sure, the gradient does tell you that, but you can't call that change density because we're not going that way. We're going this way, right? As far as we're concerned for our calculation, how steep the mountain is in the uphill direction, not the same as how steep the mountain is in the direction we're going, right? Nevertheless, the gradient, by way of its magnitude, is telling you something fundamental about how the function's changing. But the gradient is always also telling you something else. The gradient is also telling you what that maximal direction is. What is the uphill direction? So it's giving you not only a rate of change, not only a density, it's giving you a direction. What I like to call in this context an orientation. So I like to think of the gradient as being an oriented density. It's an oriented thing with a direction. That direction has meaning. It tells you how, independent of your personal experience, how is the function changing? And by its magnitude, how much is the function changing? But because it is oriented, because it's an oriented thing, you have to dot it with your actual tangent vector of interest to get the density. Okay, so the idea here, I think of the gradient vector as being an oriented density measuring change, of course. So oriented change density, it's a vector. It's telling you in some sense more than just the density. It's also telling you the orientation of the density, and thus requiring a dot product to get your actual density. All right, so you can see why I didn't want to talk about this when I was talking about flux density and change density and Green's theorem circulation density, because those are scalar quantities, and this is this vector aspect to it is a completely different thing, and I didn't want to muddy the waters. Okay, but this is the perfect tool for understanding curl, as it turns out. Now, let's think about what we've got here. Now, we understand how functions change, and we understand level sets, and gradients are perpendicular level sets. Gradients point in the direction that the function is changing. Gradients, by their magnitude, tell you how fast the function is changing, and then how that affects you personally. Okay, that's your problem. Dot with your tangent vector if you want to make it relevant to you. Curl is totally analogous. And here's the picture. Suppose you have a vector field that is circulating. Let's see, I want to do this in. Yeah. So this is my attempt to draw a vector field that represents the flow of a fluid that's, kind of. You could imagine the air kind of circulating around, if you will, this axis, right? If you think about it in 3 dimensions, if something is curling, if a fluid is circulating, it's circulating around an axis. There is a direction to circulation. Now, that's not true in 2 dimensions. In 2 dimensions, there's only one way around which a fluid in 2 dimensions can circulate. It's going to circulate. There's no room to go around different axes. Right? There's just one direction. So circulation is a scalar quantity. But in 3 dimensions, right, it's circulation will be around an axis. So curl tells you 2 things, just like gradient does. It tells you by its magnitude, it tells you how much the fluid is circulating. So if you have a short curl vector, then that means that the circulation is slow. This is not that much. It's slow flow around that line, right? If the curl is long, that means that there is a fast circulation of the fluid around that line. So the magnitude of the curl tells you how much circulation, and the direction of the curl tells you the axis around which the fluid is circulating. The analogy is very strong. The direction of the gradient tells you, which way the function is changing. The magnitude of the gradient tells you how much or how fast the function is changing. The direction of the curl tells you in which way the fluid is circulating. So around what axis? Right, that's how we talk about how things circulate, is around what axis. In what direction is the fluid circulating? And again, the magnitude tells you how much. So the analogy is very strong. I want you all to chew on this comparison. Think about how you see this oriented aspect of how the fundamental theorem of line integrals is written, how the gradient interpreted as an oriented density, oriented change density. And it's the same story with curl. Let me go back up to, here's the algebra. So in the same way that, circulation is computed like this, there's the density, right? Circulation per unit area is simply not curl. It's curl.in, right? So that leaves curl as being an oriented thing, oriented circulation density, I like to call it. And dot product with the normal vector tells you the specifics as it pertains to your particular situation. The actual piece of surface that I'm interested in circulation around. Okay. Again, just like with Green's theorem, just like with Green's operator. Green's operator, I like to think of circulation density, but it's commonly referred to as vorticity. Likewise, curl, I like to think of as oriented circulation density, commonly thought of as vorticity. Same deal. How much is the fluid spinning around, and around what axis is it spinning? Okay. All right. So there's a lot to say about that. I am going to skip all the physics at the end of 6.5. It makes me a little sad because this is really interesting physics, and I encourage y'all to read this. For those of you who are engineers, you're not getting away from this. You're gonna see this physics for sure, right? When you take a second semester physics class. So I would encourage you, while you're here, while the Stokes' curl theorem is fresh in your mind, read up on these connections to physics, and you can see the obvious connections in the way this theorem is written down. This is one of Maxwell's equations. That it's about the curl of the magnetic field, and a related version of which, if you take a flux of both sides. Take a flux of both sides of this equation, you end up with a alternative version here about circulation. All right, so there's some really important connections to physics, how magnetic fields relate to current fields, flows of charged particles, and let me just point out the grammatical similarities to when we were talking about the physics applications of Gauss. In the same way that this is a statement about circulation, this is about circulation density. All right, so it's very, very similar to the connections that we made with Gauss's divergence theorem as being, on the one hand, the statements about flux, and on the other hand, statements about flux density. Okay, anyway, that's for y'all to read on your own. Again, another version of this Maxwell's fourth equation worth looking at. Okay, so I'm going to move on to section 6.6, path independence. This goes back to the fundamental theorem of line integrals. So arguably this is, this dials us back in time to, way long time ago, of about a week ago, when we were talking about the fundamental theorem of line integrals, right? And so there's a strong connection between the fundamental theorem of line integrals and this idea of path independence. So first, let me remind you what the fundamental theorem of line integral says. Here it is. Right now, again, yawn. We saw this a long time ago. What I want to point out is that there is something actually quite peculiar about what this says. Shockingly peculiar if you think about it from the right point of view. What this says is, okay, I've got this curve, and let's ignore this curve here. Let's just look at this one curve there. Right? I'm interested in computing a line integral over that curve. Now think about how we define a line integral. We've got to take this curve, we have to chop it up into little pieces, and on all of these little pieces we've got to do a certain calculation. I've got to look at that piece. and look at what the vector field is doing there, and take a dot product with the dx vector, and then I've got to look at this piece and that piece, and I've got to look at all these individual pieces. This calculation here happens over the entire curve. And the theorem, though, says, yeah, no, you don't really have to look at the whole curve. You can just look at these endpoints. You can do a calculation that only takes any consideration at all of the endpoints. Well, it seems almost implausible, right? How could a calculation that takes place on a curve not require looking at the curve? Right? I mean, it seems utterly implausible. Okay, now, okay, right, fine. But now, let me go ahead and pull the curtain back. Of course, it's not really implausible. It's a trick, right? The fundamental theorem of line integrals is a trick. The reason that we can get away with this is that it's only certain vector fields. It's only gradients, right? Over which this statement is true. If the vector field's not a gradient, then the trick falls apart. It's a trick. Right? So tricks have catches. So it's got to be a gradient. And because the way this trick works, of course, is that by being a gradient, even though we have to look at calculations that naively we would do on little pieces of curve, that calculation on that little piece of curve is simply just measuring how much a certain function is changing, and that this function, changes in this function, are fundamentally accumulating quantities, and so we can do the calculation just on the endpoints. So, right, I mean, it works. It's, this is all old news, but I do think that's really surprising. So, let me point out a consequence of this, and that is that if I were to look at that curve, C1, and if I were to look at this totally different curve, C2, starts and ends at the same point, right? The line integral on C1 and the line integral on C2 will have the same value. This blue line integral and this green line integral, they have the same value, even though those line integrals are done on completely different curves, because, again, we're just measuring how much is the anti-gradient changing. How much is our altitude changing between starting point and ending point. It doesn't really matter what path you do your hike. The grand total change in your altitude just depends on where'd you start, where'd you end. Right? Said differently, both of these things are equal to that. Right? So, punchline, when two curves start and end at the same point, a gradient line integral doesn't depend on the curve. You can wiggle however you want. The wiggling in the middle doesn't make any difference. It's only the starting points and the ending points. Okay, so this is a remarkable property of gradients. Gradient fields have this feature, and we're going to write this down as a property. This is called path independence. A vector field is said to be path independent if it has this feature that we were just talking up, namely, as long as these two curves have, whoops, I circled the wrong thing. As long as these two curves have the same starting point and ending point, the line integrals will always be equal. Right, so you can see that this property is satisfied right here, right? Gradient fields are path independent. Okay, so now here's the natural next question. We see that gradients have this property, right? In fact, we came up with this as a property. We came up with this as a subject of a discussion by noticing that gradients have this feature. That it doesn't really matter how you walk. As long as you start in the same place and end at the same place, the path doesn't matter. Does any other kind of vector field have this property? Are there things that are not gradients that are still somehow, for other reasons, necessarily still path independent? And that's a hard question if you think about it. Right. So anyway, it's I don't have time to go ahead and talk about the whys, but the answer to that question is no. We've already observed that if it's a gradient, it's path independent, and I'm going to state here, for your free use in this course and beyond, that every path independent every path independent vector field is a gradient. And let me emphasize here, by the way, I'm sweeping under the rug issues about regularity. They are very important, but there's enough going on as it is without worrying about discontinuities and singularities and stuff like that. So for the purposes of the discussion, every vector field, every function, defined everywhere, infinitely differentiable, no regularity issues. We're not going to worry about that to speak of in this course. So every gradient is path independent, and every path independent is a gradient. Now one example of how we can use this is this is a little bit of a manufactured example, and I'll explain why I had to manufacture such a weird example in a couple of minutes. But suppose we have this vector field. Notice I'm not giving you the formula for P, Q, and R. All I'm telling you is that this first component P has a factor of Z in it. That's all I'm going to tell you. Right? Okay. And suppose that we know, furthermore, that this is a gradient of some function f. And that's all I know, right? I know that the first component has a factor of Z, and I know that this vector field is a gradient of something. And with that being given, I want to compute the line integral of this vector field over that curve. And this looks like a nightmare of a question because, yikes, look at that vector field, right? It's got a sixth power in it, and an exponential, and it looks very unfriendly. And I don't know P, Q, and R, so it seems hopeless. Turns out there's a real clever way to approach this problem. Let's think about this curve. Note that it starts and ends at points that we can compute. Right? We can take t equals 0, plug it in. We can take t equals 1, plug it in, see what we get. And this curve starts and ends at these 2 points. 0, 0, 0, and E, 0, 0. Did I draw a picture of this? I did not. Okay, so let me sketch what this curve looks like then with a very, very bad, rough approximation. This curve, right? Well, it starts there and it ends there. So this curve looks kind of like that or something. I don't know. Right? Wacky curve. But I know where it starts and I know where it ends. Okay. So here's the big point, though. I know that this vector field is a gradient. Knowing that it's a gradient means I know that it's path independent. Knowing that it's path independent means I can change the curve to any other curve that I would like as long as it starts and ends at the same point. So that's huge, right? The fact that this is a gradient means change the path however you'd like. Again, you've got to respect the starting and ending points. So again, maximal creative laziness. What curve can I think of that starts there and ends there and makes my life as easy as possible? I like this one. Straight line right along the x-axis. Everybody on board? I can just change the curve like that. All right, I cite path independence. My responsibilities to the original curve are pretty much gone. Starting point and ending point. All right, so let's get rid of this ugly monster there. Now, there's our curve. Now our life's starting to look a lot better. By the way, so some really good things happen on this curve. On that curve, notice that, well, two things. The derivative along this curve is really easy to write down. Right, as I'm moving along that curve, there's your derivative. Easy to parameterize. That's x prime. Second thing you'll notice, and this is an important observation, on this curve, notice that z is always 0. It wasn't on the original curve, right? But we're done with that original curve. We've gotten rid of him. We're looking only at this new curve now, and on that new curve, z is always 0. Which I can plug into there, and I'm taking an integral of 0. And therefore my integral is 0. So we just computed a great big nasty integral. Now, again, this question again is highly manufactured. You look at the statement of this question. What are the odds that you're going to actually know exactly this information? That you're going to know that the first component of the field has a factor of z, and you know that it's a gradient of something? It doesn't tend to happen most of the time. So the reason I had to do this is because I wanted an example that could really only be done by using path independence. So what am I talking about? Here's the thing. If I just wrote down some generic vector field that is known to be a gradient, right? I wanted to be able to use path independence. That means that what I write down has to be a gradient. And that means I could just use the fundamental theorem of line integrals, right? And students always want to know, why do we need path independence? Path independence automatically tells you have a gradient. That means that you automatically know that you can find an anti-gradient, and that means you can just plug into this. We've got this great big baseball bat of a theorem, fundamental theorem of line integrals. Why don't we just use that? Right? Does everybody see the point here? So for one thing, I just wanted to show that it doesn't that reasoning doesn't always apply. You can manufacture such examples. But the big thing I wanted to get to as to why that argument doesn't fly is to remind you that we're not in math always simply interested in computing things. Right? Math is not about compute. I mean, that's an important feature of math. But another thing that's really important in math is just understanding ideas, understanding how things connect to other things in maybe unexpected ways. And path independence is even though it's simultaneous with being a gradient, as a concept, it's a very different concept. And that makes it useful. So let me show you another way in which this is useful that doesn't have anything to do with computation. It has to do with potential energy. And I know this is a physics thing, but it's a great answer to the question. So y'all are aware of this idea of conservation of energy. Not in the environmental sense, but in the physics sense, right? So kinetic energy plus potential energy, constant. Right, so I can take this stapler, right? Up here it has a lot of potential energy, no kinetic energy because it's not moving, right? If I were to drop this stapler, it would come down and I'd catch it with my other hand. When it hits my hand here, it would have less potential energy because look, it's down here instead of up there. Less potential energy, but it would have more kinetic energy, right? It hits my hand it's moving out pretty fast when it hits my hand. So grand total, and this is a very important idea in mechanics, potential energy plus kinetic energy is a constant. That's a powerful idea. Now let's talk about this idea of potential energy. Where does potential energy come from? Potential energy comes from the idea of, well, suppose I'm here and I want to get up to here. The difference in the potential energy at this point and this point is, well, how much work does it take to move from A to B? Work is measured with a line integral. I need to know how much work does it take to move along that curve. But also, I want to know that when I talk about the potential energy at this location, I would like to know that that depends only on the location. Potential energy needs to only depend on where something is, not how it got there. So that means that the work calculation along any line integral from A to B, these have to give you the same value. So if you're going to have an idea of potential energy at all, Right? If you're going to be able to do, I mean, again, this is one of the most important ideas in mechanics, is that total energy is conserved. For that idea to fly, you need to have a notion of potential energy. To have a notion of potential energy, you need for these work line integrals to all equal to each other. So said differently, you need for the gravitational field that you're working against, it is essential that the gravitational field be path independent. So it's extremely important as a concept. Notice I didn't compute anything in this guy. Or this is just talking about how ideas, important ideas relate to other important ideas. I mean, powerful computational tools come from understanding ideas. Ideas come from understanding other ideas. And path independence is a really, really important contributor to this sequence of ideas here. It all, in some sense, comes back to that path independence. Okay. So I'm out of time. I will pick up here on tomorrow. We're going to have to cover a lot of ground tomorrow. We're running out of time in the class. We'll make it. We'll get it done. See y'all later. Oh, by the way, a quick announcement. I'll go ahead and stop.